we're going to talk about the concept of apparent luminosity. We talked at great length about absolute luminosity, which is how bright a star is. Now we talk about apparent luminosity, which is a measure of how bright it appears to us, right? So if we are the Earth here, and there's a star over here, how bright does that star appear to us? Well, it depends on how bright it actually is, the absolute luminosity of the star, divided by its distance from us squared. So the apparent luminosity is proportional to the absolute luminosity over the distance squared. Where does that concept of the distance squared come from? Well, because the beam of light that radially emanates away from the sphere emanates as proportional to the surface area of that sphere, right? The light that the star is giving off radially emanates away like this, like this, like this. Right? So by the time that the light reaches us, it is a certain distance away from the star, and the surface area of that sphere over which the light has spread out, the surface area is proportional to the radius of that distance squared. Okay? You remember how we talked about the luminosity of a star? L is proportional to r squared t to the fourth. And I said the reason that the Stefan-Boltzmann law works is because the surface area of a sphere is proportional to the radius squared. Well, this is the same concept, except it's in a different way. We're saying the brightness of the star will be diminished proportional to the surface area over which that brightness has been spread out, right? So the farther away we are only a portion of that sphere that the light has spread over. So that's where the distance d comes from. The distance d is the same as the radius. So this is the radius of the sphere, and that's equal to the distance d that we're calling it, okay? So, how can we use this law, okay? Well, here's what we can say. Right now, the Earth is 1 AU away from the Sun. The Earth is 1 AU away, and here's the Sun. Let's call the luminosity of the Sun 1, and we are 1 AU away. So the apparent luminosity of the Sun, as we see the Sun right now, is what? Well, 1 over 1 squared. So we'll call the apparent luminosity of the Sun 1, because 1 squared is 1, right? 1 over 1 squared is 1. Now, what would have happened if we were next to the same Sun, but we were 2 AUs away? How bright would the Sun appear then, as compared to how bright it appears now? The apparent luminosity would be equal to what? Well, if it's still the same brightness, it'll be 1 over 2 squared, right? So it's going to be 1/4. Therefore, it will be it will appear a quarter of the brightness as what it appears now, which is to say, it will appear 25% the brightness of what it appears now. So notice, just by moving 2 AUs away, we've cut the luminosity by 1/4. So it only appears 25% of its present luminosity. What if you go to 3 AUs away, 4 AUs away, 5 AUs away, right? So by the time you go to 5 AUs away, let's say this is 5 AU, I'm not drawing it to scale. Well, that will actually be the distance of Jupiter from the Sun. Jupiter is actually 5 AUs away, roughly. So how bright does the Sun appear from Jupiter as it does from the Earth? Well, the apparent luminosity is what? 1 over 5 squared, 1 over 25. The Sun only appears 1/25 as bright from Jupiter as it does from Earth. And then if you change that to percentage, that's 4%. So the Sun appears only 4% as bright as it does from Earth. So you can tell now why Jupiter is a very cold place. As you move out to 3 AU, 4 AU, 5 AU, the temperature of the planet drops pretty rapidly. By the time you go to Jupiter, it's already a very, very cold place. By the time you go to Saturn and Neptune and so on, of course, it's going to be very, very cold. The other kind of question I can ask here is this. What if we were living next to another star, okay? let's say one day we go to another solar system, we discover a solar system, and in that solar system, their star is 10 times brighter than the sun, okay? 10 times brighter than the sun. So we'll say star here, okay? If we now go 1 AU away from that star, okay? If you think about this, this might be a likelihood in the future. We discover that our star, our sun is going to die, and therefore future explorers go and look for another solar system. They drag the Earth, or maybe they don't drag the Earth, they just go to that solar system and they happen to find the planet that is habitable, and they live around that planet that is 1 AU away from that star. Okay? What will be the apparent luminosity? Well, if it's 10 times brighter over 1 squared, that star will appear 10 times as bright as it does from Earth. What will the temperature of that planet be? It will be pretty hot, right? Maybe even not bearable. If the sun appears 10 times brighter, the temperature will be much hotter, and so maybe you wouldn't want to live there. What if you live 2 AUs away from that 10 star? Okay? Now what would be the apparent brightness? Okay, so it would be 10 over 2 squared. Okay, now it's a little bit better because you have 10 over 4, and that will be 2.5. So if we go and find a star that's 10 times brighter than the sun, and we live 2 AUs away from that star, that star will appear 2.5 times as bright as our sun appears. So it is brighter, but not that much. Well, what if we live 5 AUs away? Well, then you can see 10 over 5 squared, 10 over 25, and then that's going to be what? That's going to be 40%. 40% as bright as it appears from the Earth. So now the planet will be too cold. So maybe the question can be worded this way. If we happen to have a choice of where to put our Earth, how far away should we put it from that star so that the temperature of that planet will be very similar to what it is now, right? So let's say we happen to find a star that's 10 times as bright as the sun. How far away should we be from that star so that the apparent luminosity of that star will exactly equal 1, the same as the apparent luminosity now? So we say apparent luminosity is 10 over d squared. So then d goes over there, d squared is 10, d is equal to square root of 10, roughly 3 point something something AUs. Okay? So that means if we discover a star that's 10 times brighter than the sun, we should be about 3 AUs away from it so that the temperatures there will be very similar to our Earth temperatures. What if we discover a star that's 100 times brighter? Okay? Well, now we're going to have to go a little farther, right? So we're going to have to go 100, d squared, 100, 100, and now how far away should we be? 10 AUs away, right? As a matter of fact, this is actually called the habitable zone. Whenever there is a star, let's say it's 100 times brighter than the sun, there is a zone around that star where we can find water in its liquid form. So the temperatures are similar to the temperatures on Earth. So if we discover a star that's 100 times brighter than the sun, what is the habitable zone? Well, it's about 10 AUs. 10 AUs. Maybe we could be at 9 AU all the way to 11 AU. There's possibly a range. We can come in a little bit closer. The temperatures will be hotter. We'll go a little bit farther. The temperatures will be colder. But you can't go too far too close because then you will not be in the habitable zone. Okay? So now you can see various kind of questions I can ask. I could give you a star with a certain brightness, a certain distance, and I can say how bright does that star appear as compared to Earth. Let's say 10 and 2. Or I can say how far away do you have to be so that the star appears just as bright as the Earth. Now here's a third way the question can be worded. Star A, let's say star A is 1,000 times brighter than our sun. So it's really, really a bright star. But the distance of star A from us is basically, let's say it is 1,000 light years away, right? And now star B is 50 times brighter than the sun. So it's not that bright. This is a lot brighter. But the distance of star B, okay, is 10 light years away. So it's 1/100th the distance of this star. So which star will appear brighter to us? So if you go out at night and you are able to see both stars with your naked eye at night, which star will you say looks brighter? Oh, star A looks brighter or star B? So how do we calculate this? Well, we apply the same equation. The apparent luminosity of star A is, since its luminosity is 1,000 and its distance away from us is 1,000 squared. So its apparent luminosity is 1,000 over 1,000 squared. It's not actually equal to, it's proportional to that, but for our sake we can just say equals. So then what is that? 1,000? Well, actually basically this one cancels one of these and you get 1 over 1,000, which is 10 to the minus 3, 1,000th, right? So basically 0.001. Okay, what's the apparent luminosity of star B? The apparent luminosity of star B, 50 over 10 squared. Okay, so then this will be 50 over 100, and that's equal to what? That's equal to 0.5. Wow, that star will appear brighter. Its apparent luminosity is quite larger than this one, right? So the apparent luminosity of star B is much more than the apparent luminosity of star A. So even though this was 1,000 times brighter, but because it was 1,000 light years away, it will appear much dimmer. Now, how about if it was 100 light years away? And that was 10 light years away. Now which one wins? Well, I put here 10, I will put here 100 and I will square it. Now what's going to happen? Okay, well now you have 1,000 divided by 1, 0, 0, 0, 0. 3 zeros will cancel these, 1/10. So that's going to be 0.1. That one still wins. It's about 5 times brighter looking than this star, right? 0.5 versus 0.1. So the 50 luminosity, 10 light years away, beats the 1,000 luminosity, 100 light years away. That's pretty interesting, isn't that? This is a lot brighter than this, and it's only 10 times farther away, yet this appears brighter. So you can see, we can do all kinds of combinations. If I bring this in a little closer, then this one will start getting closer to 0.5. Eventually, this one will beat that one. For example, if it is 80 light years away, you can try 1,000 over 80 squared. It will most likely beat that one, or maybe even less than 80, okay? So you can kind of see now how this law is useful in comparing the apparent luminosity of different stars to each other and saying which one is brighter, and also asking the question, where is the habitable zone of a star? How far away do I have to be so that the star appears as bright as our sun appears, okay? Thank you very much.